Hey geometry students, today we are going to cover some important postulates or axioms that are the foundation of pretty much everything that we do in geometry. Your book numbers them. That's a fairly arbitrary thing. It's not like if you're reading a different textbook that they would have the same order. But we have already covered a couple of major postulates already. We know the segment addition postulate, and that says that if I've got a segment with a point on it, we'll call it B, then AB plus BC is equal to AC. So this is the segment addition postulate. We also have the angle addition postulate. So if we A, B, C, and D, we know that angle ADB plus angle BDC would be equal to the total angle ADC. And so these are two of the common first postulates that you run across. There are a number of postulates that give us the foundation for geometry. And today we are going to cover a number of those. And so we'll just kind of go over them. I've numbered them as they are in our textbook, but know that that doesn't exactly stay through every textbook. So number 5, I suppose, is that through any 2 points there exists exactly one line. And we'll draw some pictures down below to help clarify things. So if I have 2 points, well, how many straight lines can I draw through these 2 points? Well, you can see there's just one. Okay. A line contains at least 2 points. So I can have a fairly close together line. I can get as close, I guess a segment, I can get as close as I want, but I have to have at least 2 points. If I only have 1 point, well, then it's zero dimensional. I can't get that first dimension unless I have 2 separate points to go into. So a line contains at least 2 points. Number 7, if 2 lines intersect, then their intersection is exactly 1 point. So again, we're talking about lines here that are straight lines. Obviously we saw last year with parabolas you could have 2 intersection points, but when you've got 2 straight lines and they intersect, well, there's that's why it's an axiom, that's why it's a postulate. It's pretty self-explanatory. I can't have any more than 1 intersection point. Number 8, through any 3 non-collinear points, there exists exactly, so if I have 3 non-collinear points, there exists exactly, well, 1 plane. Okay, so the other way of saying this is a plane contains at least 3 non-collinear points. And of course, the way that with 8 and 9 is this keyword non-collinear. So be on the lookout for that. This comes up in a lot of examples or counterexamples, really. Because people just always kind of assume that the author is intending for them to be non-collinear, but of course they could be. And so here I have 3 collinear points that of course don't make a plane. So the keyword there, non-collinear. Number 10, if 2 points lie in a plane, then the line containing them is also the plane. So if I've got some sort of plane and 2 points lie in that plane, well, then my line that connects them must also be in that plane. And then we saw this in chapter 1. If 2 planes intersect, then their intersection is a line. So if we drew the box, we could definitely see that if I have 2 planes intersecting, their intersection is a line. 3 planes could intersect at a point or a line, but 2 planes intersecting, their intersection is a line. I'll just also take this moment to talk about Euclid's fifth. Now, Euclid did number his, and generally those go in order. Okay, so Euclid's fifth postulate is a very important postulate because it was widely debated. No, people didn't really accept Euclid's fifth postulate as an axiom, as something that didn't have to be proven. And actually this spawned other types of geometries. You know, we work with plane geometry here in your 8th grade or even your 9th grade year. But later on, there are multiple types of geometry, primarily spherical geometry. And in spherical geometry, Euclid's fifth postulate doesn't hold true. So Euclid's fifth postulate is simply that if you have a line and a point, so if we call this L and call this P, there exists exactly one line through P that is parallel to L. And so, yeah, there are definitely circumstances where that's not the case, but all of those wind up being different types of geometry. In plane geometry, it holds true, though. All right, moving on to some examples of what you will see in this lesson regarding these important postulates. Okay? So, example 1, decide whether the statement is true or false. If it's true, then state the postulate that proves it. And again, we've numbered them, so you can just use those, refer back to them. If it's false, draw a counterexample. So, if we have points A and B, and they're in plane P, AB is also in plane P. Well, that actually sounds quite a bit like number 10. If 2 points lie in a plane, then the line containing them is also in that plane. So we'll just say postulate 10. And actually, for your test, I will post these for you. All right, points A, B, and C make a plane. You would think, can I come up with an example where points A, B, and C make a plane? Of course you can, but the key is, can we find a counterexample to this? And of course we can. Here would be a clear drawn counterexample. Here's points A, B, and C. They don't make a plane. They make a line. They're collinear. And so, here's my counterexample. False. Okay. Moving on to, well, looks like that's about it. So, that's what you'll see with important postulates.